a quantum system that cannot be solved exactly, but for which we want to use the variational method. But instead of just making the parameter in the variational method be some part of the function, let's do it the following way. We're going to write our trial wave function as the linear combination of two other functions. Now, these two other functions need not necessarily be orthogonal to one another. They need not necessarily be eigenfunctions of another operator. They're just functions that we want to use to construct our trial wave function. The parameters now are the expansion coefficients themselves, so it's a little bit different than what we saw before. Now, when we construct our expectation value for the energy, that is going to end up being something that is a function of these two expansion parameters. So when I write this out as an integral of phi trial h phi d tau and divide this by phi star trial phi d tau, this will be our energy expectation value. And if I write phi trial as a linear combination this way, you can see where the A1 and A2 are going to come into play. So let's figure out what these different parts will give us. So first, the numerator part. Okay, so this is effectively taking A1 phi 1 plus A2 phi 2 h A1 phi 1 plus A2 phi 2. So if I expand all of this out, I can show that in fact what I'll get out of this is something that looks as follows. A1 squared times phi 1 h1 phi 1 plus A1 A2 times phi 1 h phi 2 plus A1 2 A1 times phi 2 h phi 1 plus A2 squared, and I'm running out of room here, times this. So the net result here is a long expression that involves these expectation values of the Hamiltonian sandwiched between two different basis functions and these coefficients A1 and A2. Well, these numbers here, these are just numbers. And in order to simplify our notation, I'm going to express these as follows. If I have h sandwiched between phi I and phi j, I'm just going to write that as h sub ij. So it's a number, but it's a number that has a specific prescription for how to calculate that number. It's an integral of the Hamiltonian operator sandwiched between two of the basis functions. And since the basis functions are not necessarily eigenfunctions of the Hamiltonian, these are not necessarily numbers that we can immediately write down, although hopefully we've chosen basis functions that will allow us to calculate those fairly readily. I also want to define, for example, just the overlap of phi I, phi j as a number that I'll call s sub ij. Okay, so again, this is numbers. So when I look at the denominator here, this can be written very succinctly as a1 squared times s11 plus a12 times s12 plus a21, a1a2 plus a2a1, times s21 plus a2 squared times s2, 2. All right, so now I'm going to take this stuff down here, multiply it by the energy, and set it equal to this stuff. So I'll have a1 squared h11 plus a1 a2 h12 plus a1 a2 h21 plus a2 squared h22 is equal to E times a1 squared s11 plus a1 a2 s12 plus a1 a2 s21 plus a2 squared s22. And I've written this out in excruciating detail just to show you that it's not an impossible thing to write down. It just takes a while to do so. All right, so now what am I after here? I need to find values for these coefficients. I also need to find the minimum value for this energy. And it turns out that this, written this way, it's hard to tell, but this is another form of an eigenvalue equation. It's a linear eigenvalue equation, which means that it can be written as a matrix eigenvalue equation. Now we'll talk about that a little bit more in another video, but let me just show you sort of where this leads us. If I were to subtract all of these terms from these terms and collect terms that have similar coefficients, I would have a1 squared times h11 minus e times s11. Then I would have a1, a2 times h12 minus e s12. I will also have a term that would be h21 minus e s21, and a term that is a2 squared times h22 minus e s22. And all of that would be equal to 0. So this looks like a big old complicated thing to solve. It turns out it's going to be a little bit easier than it looks. Okay, but what we need to do first is to optimize this result. This will give us indirectly an expression for the energy that we need to solve for. But we get there by optimizing these variational parameters. So I need to take the derivative with respect to a1 of all of this stuff. And what I'll get is the following. I'll get 2a1 times h11 minus e s11 plus a2 times h12 minus e s12. But now I'm going to claim that because the Hamiltonian operator is Hermitian, and also these functions can be written in either order for S11, that this term here is the same as this term. So in other words, I'm just going to get 2 of this same term when I take that derivative with respect to A1. Okay, and there's no dependence on A1 over here, so that's just equal to 0. When I do the same for A2, I will end up with a similar sort of expression where I'll have 2a1 times h12 minus e s12 plus 2a2 times h22 minus e s22. All right, well, the 2's are immaterial. We can divide through by 2 and simply have one term times a1 plus another term times a2 is equal to 0, and then the same down here. Now, if this were simply an xy, if this were simply a pair of linear equations in x and y, it wouldn't be very much fun to solve this because we would just say, well, a1 is equal to a2 is equal to 0. And that's the answer. And that is a possible answer here. But this is something we call the trivial solution. Trivial because it means there's no trial wave function. If both of these coefficients are equal to 0, there cannot be a trial wave function. However, I'll tell you that there is a possibility that we could choose a value for e here that would cause this equation to have a real solution, a non-trivial solution. So let's see where that comes from. All right, so when I write these things down, I'm going to have h11 minus e s11 times a1 plus h12 minus e s12 times a2 is equal to 0, and h12 minus e s12 times a1 plus h22 minus e s22 times a2 is equal to 0. Now, if these numbers were such that these were two independent linear equations in x and y, or a1 and a2, then there would be only one solution, and that would be the trivial solution. However, if it turns out if this number times this number is equal to this number times this number, then these are not linearly independent equations. And in fact, they're in that particular instance, then there can be solutions for a1 and a2 that are not 0 and 0. Well, what I've just described is the equivalent of taking this determinant of a 2 by 2 matrix. And I'm still writing this all out in excruciating detail so you can see exactly what you get for all of this. Well, this is a very special equation. This particular object here is called the secular determinant. And what I want to point out here is that all these numbers, h11, s11, h12, s12, all of them are numbers we can calculate from things given in the problem. The one we don't know is the energy. So in other words, we want to solve this equation for the energy. And when we do that, then we'll have two linearly dependent equations up here, and we'll be able to substitute our expression or our value for the energy that we get from solving this equation to find a linearly independent solution where A1 and A2 are not both equal to 0. Now, this is an example of a matrix eigenvalue problem. And it turns out because there's 2 rows and 2 columns in this, there will also be 2 solutions for E. Okay, which means that from those 2 solutions for E, we can get 2 sets of values for A1 and A2 that will satisfy this. In other words, we're going to get 2 different trial functions. One which is the first solution times phi1 plus the first solution of this times phi2, and another which would be the second solution from the eigenvalue equation. All right, so when we go to this, we actually will be able to derive 2 different energy levels and 2 different solutions. Okay, what we'll care about, at least initially, is just the lowest energy solution of those 2. And we'll see in the next video how this gets generalized to even greater numbers of expansion coefficients and greater numbers of expansion functions to solve for even more energy levels.